Hi, everyone. I want to talk about a very exciting paper that popped out a couple of days ago, which is talking about Convnet versus Transformers supervised versus clip beyond ImageNet accuracy. This is an amazing work done by those authors. So the story of this work starts that the computer vision landscape has become very complex. We have many different architectures, many different Convnet variants, many different vision transformers, and also their variants. And we also have different training paradigms. We have a supervised training paradigm, kind of the old paradigm that started with ImageNet and maybe before. And then we also nowadays are very interested in a clip training paradigm that also emerged as a new training paradigm to align maybe vision and language. And now the question becomes which model should we use, which model is better, and why. So generally, this has been assessed based on one metric, which is the ImageNet accuracy metric. So the idea is that you would run your model. If you get better ImageNet results, you're happy, your model is good. However, this metric is becoming overly saturated because you're kind of overfitting, your model is kind of overfitting to ImageNet, to the intricacies of the ImageNet. And it specifically does not consider other metrics that are important, like the training way, the data type, the architectural paradigms. And it would be really cool if we can devise metrics that will give us insights into why a model is failing and not succeeding, because that way we could use this metric to further improve our models. So now the models themselves, they could, for example, do really similarly on this ImageNet tasks, but they could be different on very different types of metrics and aspects. So this is what the paper argues. What the paper would like to do, they would like to understand over an array of different metrics the performance of some of the latest computer vision models. So they want to understand their shape biases, how well they do on synthetic data, what type of mistakes they do, what about calibration? Are they robust? Are they transferable? Can I transfer? Can I use these models to do correct transfer? What about invariances? Which model is more robust to invariances? So they made the following design choices. The first design choice is they picked the Convnext to represent Convnets, and they picked the vision transformer, and also they considered supervised and clip-based training. The reasoning is that those models have similar parameter counts and they have similar accuracy on ImageNet 1K, so therefore it's a fair comparison to have. Importantly, they assess pre-trained models out of the box, and they don't want to consider what happens when we do additional fine-tuning. So it's kind of out of the box behavior. What do you get from those models if you just take them as is? So the first thing they wanted to understand is the type of mistakes. For that, they actually ran their experiments on ImageNet X, which is a data set that has 16 factors of annotations from a human, like a pose, a style, and so forth. And then they measured the error ratio, which is defined for a factor as 1 minus the accuracy of that factor divided by 1 minus the overall accuracy. So it's like a relative overall relative performance of that factor with respect to the overall performance. And then what we could see here is that the texture is the hardest, by far the hardest for both models to get right. They have the VIT and the Convnet supervised, and VIT and Convnet clip-based training, they get high error ratios on those. On average, we can see that the supervised Convnet has a lower error ratio than the VIT supervised training, while in the clip case, we can see that on average, the VIT clip has a lower performance than the clip training. And now it's also interesting that in terms of error ratios, while they have both really similar error ratios to each other, the error ratios are much lower when it comes to the clip training compared to the supervised ones. Of course, now the who beats who here is like minor because the margins are really small, so they say that these perform similarly within each category. Then they wanted to understand what happens when we have shape or textural bias. So in order to do that, they have two metrics, and those two metrics are a shape, which is the proportion favoring shapes, and texture, which are the proportion favoring textures. In summary, the results indicate that VITs have higher shape bias. CLIP models have lower textural bias compared to the supervised ones. However, all models have a high fraction of textural decisions. So in terms of shape or textural bias, we can see that VITs will have a higher shape bias, and the CLIP in general has lower textural bias than the supervised training paradigm. And all models have a high fraction of textural decisions. Then they considered the calibration. So we wanted to understand how confident and reliable those models are. They were able to conclude that CLIP models are actually overconfident, supervised models are slightly underconfident, and supervised convnext, so supervised training of convnext model, is better calibrated than supervised VIT. So if you have a problem where reliability is important, you might really want to reassess which type of model you consider based on those results, because it seems that supervised convnext is better calibrated than the VIT in the supervised training regime. Now, interestingly, those contradict a paper that was called Revisiting the Calibration of Modern Neural Networks, and they attribute this difference to actually that this paper has used all type of neural networks and not the latest ones. They also assessed robustness and transferability. So they wanted to understand how well those models adapt to changes in distribution. So if we have a distribution shift, what do those models do? Are they robust enough to be doing well and adapt to perturbations in fog, rain, camera noises, etc., and many others? They noticed that supervised models are better than CLIP when it comes to robustness. They also found that VIT and convnext, they have similar performances on average. But what is interesting is that they found that of course, in terms of robustness, and now in terms of transferability, they noticed that convnext outperforms VITs significantly when it comes to transfer. And what is really exciting or interesting is that convnext supervised, like the supervised training of convnext, is giving us very close performance in transferability to CLIP-based training. So here we can see from this table that in terms of the overall scores, we can see that the convnext supervised training versus VIT supervised training, there's a big margin tilting towards the convnext. And when it comes to VIT CLIP and convnext CLIP, they actually perform similarly. However, the convnext supervised is close to the VIT CLIP and convnext CLIP based off performance. Then they finally considered what happens on synthetic data. So this is a type of a control experiment or a new training paradigm that's happening in computer vision that allow me to create the types of data and the quality of data I am interested in. They used this synthetic data from Pug ImageNet, and they reported those averages. What you could see is that on almost every factor here, the convnext is superior to the VIT in both training paradigms, supervised and clip-based training. In fact, there is no competition when it comes to synthetic data. We can see that the convnext is clearly winning almost all the time. In terms of average, in terms of the different textures, it might lose in a texture or two, I think, in worlds here and in the scene light, but otherwise it's winning across the board. So this paper has been roaming in Twitter, and people were excited about it. So, of course, Jan LeCun was very excited about those results. And he was pointed out, this was a nice reply, I think, that there has been another study that is comparing backbones of vision tasks, which might be worth reading itself. And of course, Jan is excited that it's hard to beat the convnexts. This is the original tweet from Zhuang Liu, and it has a nice, amazing thread on the results, I think very well explained. And this reply here, or this message inside the thread, it actually points us to the paper code if you would like to reproduce those things. However, there has been people which have been arguing, like Ali here, that, you know, convnets and VIT hybrid is better than both. So what's the point? Should we actually do that? Can we actually do better testing, right? Compared to what this paper has offered. He's also arguing that we haven't seen comparisons between the VITB and ConvNeXT-B, and he believes this is not enough to make general conclusions on which model is better than which other model. And additionally, he would be interested to see, right, what happens in downstream tasks if we further do fine tuning and so forth. So I think those are valid points. And now what we really would like to know from you, you can leave in your comments your thoughts. What do you think about this? Is this paper telling us which model we should use? Should we just go ConvNeXT, or is it still a story and a case to be made for VITs? Probably there is, but we would really love to hear from you what your thoughts are. Do leave them in the comments below. With that, I would like to ask you to like, share, and subscribe. And if you're liking the material we are doing, we would be very, very excited to hear from you in the comments below. So thanks a lot, and see you next time.